Yeah, all right. And first of all, thanks, Jimmy, for inviting me for this talk. And I'm really grateful for this. So today I will be talking about like text to image generative models and how we can make this text to image generative models more resource efficient. So before we move ahead, like let's first take a look at what are the text to image generative models. So in last couple of years, we have seen that like, oh, you can create such cool synthetic images using just text prompts. And we can do so many fun stuff that we may not have seen in the real life. Apart from just generating this text to image, there are so many downstream applications. We call it personalized text to image. For instance, let's say I have a dog named Goofy, and I want like Goofy to wear Santa's uniform or Chef's uniform, or playing at Grand Canyon or surfing at ocean. So we can do so many such cool stuff by just using text to image generative models. But how this generative models works, like, so you have given a text prompt like a photo of a small white furry dog, and we want to generate the corresponding images. And more central idea around here is the diffusion model. So you iteratively refine and keep refining the image until you get your desired image. And as we know very well that there are several state-of-the-art methods, like for instance, stable diffusion is very well known, which is the left part of the model, which uses only one particular diffusion model. And we have another popular models like the DALL-E 2 or DALL-E 3 or Kandinsky models, which use two different types of diffusion models to do this text-to-image mapping. Apart from text to image mapping, one key aspects of evaluating these models is that the compositionality. Can we generate the blue horse and brown vase together? Or can we generate a cat on top of a dog? So all of these papers, all of these recent works that trying to improve text to image generative models, all of them wants to improve this compositional understanding. So that even if we haven't seen such imaginary scenarios in real world, we can still generate it in synthetic scenario and have fun with it. Okay, but if we take a look at why resource efficiency is really important, then every day almost 34 million images are being generated using such Gen AI tools. And Google itself uses 5.6 billion gallons of water to cool down its server. And moreover, if you just want to train one stable diffusion model from scratch, it uses 10 tons of carbon footprint, which is almost equal to 10 to 15 car footprint for over the year. So how we can actually create this text to image generative model in more sustainable way? So that raises a quick flag like, okay, how we do want to create such models? So, but first of all, what contributes to the resources, like its model parameters, its data requirements, its image resolution, and of course, and last most, like its inefficient learning. So this is some of the plot, like if we look at the performance of the composition versus the parameters, then we find a trend that like if we had more and more parameters, we can see that our text to image generative models perform better and better. And more parameter means that we need more and more resources to train these models. And same applies for the downstream tasks such as personalized text to image generative models. We find that if you would just want to generate an image of my dog doing skydiving near Grand Canyon, then it takes like more than 1,000 to 100,000 GPU hours to train one such model. So it's really infeasible for us, like in academic setting or the small enterprise setting, to how we can get our own text to image generative models which takes so much less resources and we can still achieve the state-of-the-art performance. So based on this quick analysis that we conducted, we found that all of these text-to-image generative models requires more than 100 million image text pairs and requires at least 2 billions of parameters to train the model. And that is a lot. So how can we improve text-to-image mapping without requiring a lot of resources? So to work on this, like we propose a method called ECLIPSE, a resource efficient text image generative models, and we published at the CEPR 24. So I will be talking about more of this work in later this talk and how we extend it into various downstream tasks. So again, we focus on one particular design choices, which is one of the state-of-the-art models in T2I, which is the unCLIP models like DALL-E 2 or Kandinsky models. So these Kandinsky models are really unique, like because what we do is given a text as an input, we map it to the image embeddings. So text embedding to the image embedding using diffusion model. And we use this estimated image embedding to condition the stable diffusion like model to generate the corresponding images. So our goal is like how we can improve the G5, which is text to image prior. So let's take a quick look at what are these text to image prior models. So like I said earlier, that we take a text prompt, we get the corresponding feature from the text encoder, and for the corresponding image, ground truth supervised image, we get the corresponding vision embedding from the image. And then we train the diffusion model to map the text embedding to the vision embedding. Because this is a diffusion model, it requires lots of resources and lots of parameters to train. And typical training of diffusion model is like for each time step 0 to t, we iteratively refine the input and output embedding so that we get the desired images. But even this text to image prior model, like we are just working at the embedding space. Embeddings are like only 1,000 or 2,000 dimension vectors. Even though we are working on this small compressed space, we still require over 1 billion parameters and requires a lot of resources to train these models. So of course we did some analysis, like if we just want to estimate the vector, like do we really need this diffusion steps at all? So our interesting empirical analysis found that if we have more and more diffusion steps at this latent space, it actually hurts the model performance. And we can see that in x-axis we increase the diffusion steps and the performance continuously linearly drops with respect to these prior steps. And we tried to find what causes this behavior. And we found that there is an added noise term that we are adding in the diffusion model. And if we try to control this added noise, then we can still find that it's clearly linearly decreasing the performance. So how we can actually estimate like with the non-diffusion versus diffusion models. So if you look at the more approximation way this way, we find that diffusion prior loss is nothing but just a projection loss with single time step. We don't need to do forward propagation for 50 times or 1,000 times, but we can just do it in a single time step. But if we do this approximation, we lose significant performance because of the inability to do the classifier free guidance. Okay, so what do we understand from this quick comparison? That diffusion priors are slower in convergence, they require more parameters, are better at generalization, but the projection priors are faster at convergence, parameter efficient, but are not good at generalization. So how we can design a methodology that works at the like wins of both of the worlds? So we go back to the original hypothesis, like how we actually do the text to image mapping is like we use the pre-trained CLIP models. Like CLIP models are trained to maximize the mutual information between text encoders and the image encoders. So how we can leverage this mutual information between two modality in more effective way so that we can improve the text to image mapping, but also improve the resource efficiency. So what we created is like we complement the projection objective with the contrastive loss. So the CLIP models are trained with contrastive loss. So what we are doing is like we are trying to distill the knowledge from the CLIP model to the text to image diffusion model. And what an overall objective is like the projection loss plus contrastive loss. So if we take more high level look at how this helps, is that if we just use the diffusion loss or the projection loss, it may happen that some distribution shift may occur during the test time, and we may not be able to understand these distribution shifts. For instance, like orange square is not present during the training, then during the evaluation time, the model will not able to understand what orange square means, and it may try to generate either blue square or the orange circle. But with contrastive learning, we found that we can generalize to even unseen scenarios like the orange square. And that way we can even improve the performance of the text to image mapping modules. So overall, with this quick trick, we found that the ECLIPSE priors are faster in convergence, are parameter efficient, and are better at generalization. So what are the findings? So we found that by just using this ECLIPSE prior, we can compress the 1 billion parameter model to 33 million parameter. That is almost like 98% compression of the model. And if we look at the overall impact of this just prior module, we find that it compressed over 48% of the parameter of big source state-of-the-art models. Apart from just parameters, we found that because of we are doing the distillation from clip model to the text to image models, we find that we don't need more than 100 million training data set. We can just work with the less than 10 million training data set and we can still achieve state of the art performance. So if we take a look at the more of an comprehensive survey of like how many GPU hours it requires to train these models, then we find that Stable Diffusion requires more than 150,000 GPU hours, and corresponding baselines like different priors requires at least 1,000 GPU hours. And we find that Eclipse can be trained only with 50 GPU hours, which is like we can just use any of our single laptop GPU and we can train for 2 days and we can still get our state-of-the-art text to image model. And because it takes like only 30 to 34 million parameters and the data requirement is really smaller. All right. So this is the more comprehensive survey. Like if we use this Eclipse model with accordance to various state-of-the-art model, we find that Eclipse model not only compresses the parameters, but it continuously improves the state-of-the-art model, irrespective of the amount of data you use. Here we find that if you use just 0.6 million image text pairs, we can still outperform the model 1 billion parameter model trained on more than 100 million 100 million image text data set. So this was a very intriguing thought. So overall, what we found that if you look at overall graph of these all text to image models, so we find that Eclipse reduces the parameters of 72% compared to DALL-E 2 models and improves the performance of Stable Diffusion compared to 55% in the same region. So you can see that by just leveraging these better pre-training strategies, we can improve the text to image generative models. So we have, of course, for all our open source lovers, like we have released the code demo and weights everything online. And next, I will be quickly talking about like how we can extend this work for more personalized text to image generation model. So when I say personalized text to image generation model, like I said earlier, like I want my cat to wear a Iron Man suit and wearing particular sunglasses. So we can do all sorts of this crazy stuff using this text to image generative models. But again, like these models heavily require on integrating large language models with diffusion models. Because of these large language models, we very well know that they are really parameter inefficient and requires a lot of training time and resources to train this model. So how can we leverage this Eclipse model to do the actually text to image mapping? So what we did was like there no such data exists in real life where we have our dog or wearing particular sunglasses, right? So what we did was we created a synthetic data set using existing data sets such as Leon, and we created like a cat wearing particular sunglasses in the park. So we get this interleaved image text pairs, we add the corresponding features, and then we train the Lambda Eclipse model with this synthetic data set. By doing this synthetic data set, we found that these models in zero shot fashion, we don't need to do customization at all and can still do multi-concept customization. We can take 2, 3, 4 concepts and combine all of these concepts together. But even though like we can do this in zero shot fashion, we find that these models still struggle to do the state-of-the-art performance. And for the baselines, we very well have understood that Dream Boot, textual inversion are very popular methodologies and they achieve state-of-the-art performance. So we further extend the analysis like, okay, what if by using Lambda Eclipse, we further fine tune the model like Dream Boot? And we found that by just training it for 200 to 400 time steps, our model gets state-of-the-art performance. And it observes almost negligible catastrophic forgetting compared to the Dream Boot models. For instance, like let's say I have this particular dog and I want to generate this particular dog like looking backpack in some street, right? So if you look at without fine tuning, we find that it tried to generate a similar looking backpack, but the facial expression, dog expression are not really well. So if we keep fine tuning for even just 100 time steps, we find that the model quickly able to capture this new information within the images and can generalize to all sorts of different complex visual aspects. Interestingly, like we find that we can combine multiple concepts together, like a dog wearing this particular hat or cat wearing this particular sunglasses, or we can even do the dog wearing this but on top of a boat. And we found that like state-of-the-art methods like Cosmos Z or MO2 can achieve comparable performance, but they require like almost 2 billion to 37 billion parameter, while our Lambda Eclipse model is just 34 million parameters, and we can still outperform these big state-of-the-art models. At last, I want to quickly summarize like what we can do with these tools, right? So we did one quick multi-concept interpolation analysis. Like we can create and combine multiple concepts together in a very seamless fashion. For instance, like let's say this dog was wearing this hat, and we want like 50% of this hat and 50% of this hat. Then here we can see that the shape of the hat is exactly same as left one, but the color is coming from the right hat. So you can do so many such cool stuff between combining multiple concepts together. So bottom line of this work is like we can still use this pre-trained models such as CLIP to distill the knowledge for text-to-image generative models. And if we do this, then we don't need to rely on stability AI like models and or any other closed source models to get the access to these text-to-image diffusion models. We can create our own 5 million to 10 million image text data set, and you can train our own custom text-to-image diffusion models in-house by yourself. Of course, because of we are relying on the CLIP models, the limitation also comes from the CLIP model. So if we can improve the CLIP model, that means that we can directly improve the text-to-image diffusion models within 50 GPU hours. And of course, at last, like the quality of the data still matters. Like if we can improve the quality, captions, synthetic captions, that also means that we can improve the CLIP model and also text-to-image diffusion models. At last, like I would like to say thank you for again like for giving me the invitation to talk about this. And if you know where to reach out to me, like whether you can find me at my website or Twitter. And again, like I will I would leave 5 minutes to for if there is any QA.
Yeah, and it does look like there's two questions. So if you want to pop
All right.
over to the Q&A, we've got two questions.
Okay. So first question is fantastic presentation for the generation pipeline or Eclipse has focusing on projection priors being beneficial when using when building task specific generative models. Yes. So we have been working on the healthcare enterprise, and we found that like if we just use this particular prior models, then we can even leverage the healthcare data set, which is very privacy oriented, right? And these models can be trained on any hospitals or healthcare enterprise owned server, and we can still achieve the state of the art performance. So does this approach replace the concept of LoRa? So I would say we complement the LoRa's. Our method can be used with the LoRa's as well. So LoRa's is like more parameter efficient. We need to do fine tuning. But Lambda Eclipse is like, what if we don't want to do fine tuning? Let's just fine tune the Eclipse or Lambda Eclipse model beforehand, and we can do text to image generative models without even using the LoRa. But if we do that, we still find that it performance drops a bit like any other zero shot models. So if we complement it with the LoRa, then we can even outperform the Dreambooth or previous LoRa based strategies. Right. Prior to training the Eclipse model, does it rely upon the training of the prior model? No. So Eclipse model is completely trained from the scratch. So we don't need to train it like take the fine-tune model and then again fine-tune it for this clip contrastive loss. Did I hear you say that Eclipse distills a prior model, creating the starting point? Yeah. So what we do is like we take the pre-trained clip model and then do the distillation, like training from scratch using this clip as a teacher model to do the text to image mapping. Yeah, that is a good question. Like, if we count this, then clip model is also trained on millions of image text pairs. And if that is the case, then overall data requirement for prior will also increase. That is a valid point. But at the same time, like these clip models are being used for various downstream tasks. So our hypothesis is like if they are used for various like text to image retrieval, then why do we need to train text to image diffusion models from scratch? And these text to image diffusion models like Stable Diffusion 1 and Stable Diffusion XL are still using the clip models. So it's not like they are not using the clip model or T5 model. They're trained on millions of image text pairs. So overall, we can still find that we can reduce the data set dependency. That is a good question. Like, if this is a video creation, how can it work with the movies such as Netflix, right? So right now we are trying to expand our work on how to generate a video using the clip latent space. And if we can say that we have good initial hypothesis and we are trying to make it work, but we can definitely see a line like we don't need to train this text to image a text to video models like SOTA, which requires a lot of parameters, but we can still use some cool tricks that we have been known for quite some time, and we can still use the generate the video in much more efficient way. How modular it is, and what if we swap out the clip? That is a good question. So again, we have done these experiments as well. So if we know that the clip models are ever changing, right? Like what if right now we are using clip with G model, that is one of the state of the art model. But recently, like Google has also introduced the other clip models like SIGLIP model that is much more parameter efficient as well. And it achieves better performance than the with G model. But we found that we can easily tweak the prior model. So prior model requires only 15 GPU hours, right? So even if we change the clip model, we just need to train the prior model for the 50 GPU hours. We can still improve the performance if clip performance is better at the compositionality.